All right. All right, so hello everyone, welcome to the third distinguished lecture of the Soil Mechanics Foundation Division. My name is Lee Jim. Okay, so first up, let's just pop up the PowerPoint slide, right? My name is Lee Jim. I'm an associate professor from the University of Alberta. First of all, I would just like to acknowledge the land, right? So this where I am working at the University of Alberta and the city of Edmonton, right? The city of Edmonton and the University of Alberta is situated on the Treaty 6 territory, the traditional land of the First Nations and the Métis people, and we honor and respect the history, languages, and the ceremony and culture of the First Nation, Métis, and the Inuit, who call the territory home, and encourage everyone to acknowledge the importance of the land they live on. And then I would like to give a very brief introduction to the Canadian Geotech Society. The society has about 1,400 members across Canada and around the world. The Canadian Geotech Society is a driving force in the geotechnical profession by providing opportunities for members to upgrade their skills, to present research and case studies, and to connect with the other geotechnical professionals locally, nationally, and internationally. The Canadian Geotech Society has 20 local sections across Canada, 7 divisions, 8 committees, and has affiliation with the numerous national and international bodies.
Sorry, Li Jing. Why can you unmute yourself? Sorry.
That's okay, right? So yeah, Canadian Geotech Society is the owner of the Canadian Foundation Engineering Manual. The manual has become the de facto Bible for the design of foundations and retaining structures in Canada, and for many professionals and the students in Canada. And just want to keep in mind, right? The next version of the CFEM will be published online in 2023 via the Canadian Science Publishing. So just to stay in tune. And then the last slide is about the Soil Mechanics and Foundations Division. So the division is the largest internal CGS division where members can subscribe to. The mission of the division is to promote classical geotechnical and foundation engineering research, to promote documentation of case studies and experience of practicing engineers, and to promote and facilitate the continuing education of our CGS members. To fulfill this mission, the executive committee of the Soil Mechanics and Foundation divisions host a variety of events, such as the annual distinguished lecture. We organize short courses and workshops, and we support the students functions throughout the country. And we prepare technical articles for the CGS magazines, and also provide support, right, to the international societies. The executive committee currently has 13 active members, and we meet on Friday every month. So we welcome CGS members, and particularly those from the representative groups, to join the committee and to attend the committee meetings. So without any ado, so let's just begin the distinguished lecture. But now I will invite my fellow colleague, right, Dr. Chen Lin, to take over the rest and then introduce the distinguished lecture. That's all yours, Chen. Okay.
Thank you, Li Jing. I still at the meeting, some attendee, maybe you can have to keep an eye on that. It was people still joining us. Can you move on to the sponsorship?
Here we go.
Right. Okay. Thank you, Li Jing. Hello, everyone. My name is Chen Lin, and I'm a vice chair. Li Jing is the chair of Soil Mechanics Foundation Division of Canadian Geotechnical Society. I'm an associate professor at the University of Victoria. So today I'm going to moderate this distinguished lecture. First of all, on behalf of the division, I would like to acknowledge the support from the different company. So we have platinum support from civil engineering, a gold support sponsorship from Greg drilling and testing, Contact, WSP, and silver sponsor from nickel. Okay, today we are really pleased to have our distinguished speaker, Dr. Peter Robertson, to deliver the third distinguished lecture. Peter Robertson is Emeritus Professor of Civil Environmental Engineering at the University of Alberta, with over 40 years of experience as an educator, researcher, consultant, and practitioner. He is recognized as an expert both nationally, internationally in the area of in situ testing and soil liquefaction. From 1993 to 1997, Dr. Robertson was the principal investigator of Canadian liquefaction experiments, the largest geotechnical collaborative research project in Canada. He is co-author of cone penetration testing in geotechnical practice, published in 1997, a primary reference book on this subject. As a long-term Canadian Geotechnical Society member, he has served as a local section chair for both Vancouver Edmonton and chair of the Soil Mechanics Foundation Division. Among other awards, Dr. Robertson has been the recipient of AACH Bolton Cedar Medal, Canadian Geotechnical Society RM Quillis Award, and the Standard Thompson Service Award of Geotechnical Society Edmonton. He is currently a geotechnical consultant with PK Robertson Incorporated, a technical advisor with Greg Drilling and Testing Incorporated based in California. So during the presentation, I'll encourage everyone just mute yourself. If you have any questions, so you can just type the question in the chat box, and after the presentation, I will facilitate. We have a question and answer section, approximately 20 minutes. So today's the lecture title is Geotechnical Engineers Should Embrace Uncertainty. Without further ado, let's welcome our distinguished speaker, Dr. Robertson. Peter, can you share your screen?
I can, yeah.
So it's all yours.
Well, thank you for that kind introduction. It's an honor to be the third lecturer for the Soil Mechanics and Foundation Engineering Division of Canadian Geotechnical Society. I've been a proud member of the Canadian Geotechnical Society for close to 50 years now, and it really is one of the best geotechnical societies in the world, and I'm certainly very proud and honored to be a member. But maybe I do want to cover quite a bit of ground, so I'll get started quite quickly here. And so the title of the talk is that geotechnical engineers should embrace and understand uncertainty. And okay, how do I get it to go forward? That's going to be a struggle. This slide, I took the title from Professor Morgenstern, and for the last couple of years, Professor Morgenstern has been using this term that we're evolving from a period of certainty to uncertainty. And he's working on a paper that I think has that title. And I think that really captures the essence of what I'm going to try and talk about. And really that risk and uncertainty are characteristics of geotechnical engineering due to uncertainties and variability in the material properties, external loads, analytical models, and interpretations. And design approaches are evolving to account for uncertainty. And that's what I'm going to talk about here, is how design approaches are evolving, and then give some examples. And in recent years, I've been working a lot in the mine tailings industry, and so I use a mine tailings example. And when I was at the University of Alberta, I used to quite often say to graduate students that a useful thing to remember is that most of what we do in geotechnical engineering is strictly incorrect. You know, we make lots of assumptions, and often those assumptions aren't strictly correct. And so in essence, much of what we do isn't correct. The art is to get the correct answer. And that's why the evolving design approaches that account for uncertainty are allowing us to, I think, get closer to that. And so if I briefly describe how design approaches have evolved, then traditionally they were very prescriptive. In foundation design, that's often working stress design, but prescriptive in the sense of traditional design approach based on an overall factor of safety, and that modern design codes are based on these factors of safety, or for foundation design, partial safety factors such as load and resistance factor design approach. And the problem with this, it can lead to complacency and depends a lot on the competency of the designer. And it's also important to note that factor of safety is unreliable if the site has a brittle failure mode. And I'm going to illustrate that in a moment. And I've just shown an example at the bottom of a typical prescriptive design approach. This is from the Canadian Dam Association. And it sort of sets out different loading conditions and different minimum factors of safety that you're prescribed to meet. But if we illustrate, I would like to illustrate brittle failure mode. And I was involved in the investigation of the Feijão tailings dam failure in Brazil, often referred to as the Brumadinho failure because it occurred close to the town of Brumadinho. And it was unusual in the sense that, first of all, it was captured on video, and we're going to look at that video in a moment. So it was 2019 in January 25th, and it was around midday. So a sunny day, partly cloudy. Video cameras had been set up, so they were recording the dam, and so they captured this high quality video image of the failure. And the things that were to be observed was that there were no signs of distress on the dam. In fact, people were on the dam at the time, and in the center you may make out a small drill rig was drilling a hole. It had almost completed its hole down to the foundation. There were other vehicles and other people. There were some people on the lower portions, and there were also some cows that were grazing on the grass. And so no outward signs of distress. And then quite suddenly, this happened. And so you'll note that suddenly the crest drops and the toe begins to bulge, and the whole thing begins to collapse and move out extremely rapidly. And so in a period of about 15 seconds, the dam had completely failed. And here it is again. So within 15 seconds, the dam had completely failed. And within 5 minutes, 80 to 90% of all the tailings had been removed from the facility. And so this video captures the initial slide, which was a relatively shallow slide, but it extended almost the full width of the dam, and from the crest all the way to the toe. And the video camera that was set up at the rear of the facility captured the sequence afterwards, as it captures the crest suddenly dropping away. And then several seconds later, another slice comes off, because you can see from this image that there's quite a steep, almost vertical face remaining after the initial slide. And then the video at the back records the second slice falling away. And then approximately every 10 seconds or so, an additional slice would keep falling away. And the slide just slowly, retrogressively progressed all the way back until 90% of the tailings had been completely removed. So this is what I mean by a brittle failure mechanism. And so an example of a prescriptive design approach, and here's I'm showing a tailings dam. I'm not showing the actual Brumadinho. I won't discuss that one in detail because it is under litigation. And so there are restrictions on what I can say about it. What I've done instead is I've chosen an example that is very similar. It is a real project, and it's similar to several projects I've been involved in. And so this is an example of a compacted starter dam and then upstream construction using the tailings, a relatively high phreatic surface. So you've got unsaturated tailings, saturated tailings, foundation soils, and then the compacted soil. And then the prescriptive approach usually is where people have assumed an idealized cross-section, single values of parameters, and you notice almost the level of detail, the unit weight to 1 decimal place, the friction angle, cohesion intercept, and the saturated tailings, in this particular case, using a peak undrained strength. So this is an undrained analysis using the peak undrained strength of the saturated tailings and calculating a factor of safety. Here, this is not the real factor of safety, but it is close to this. But I wanted to illustrate that it's usually quoted to 3 decimal places, so 1.268. And so this clearly gives a perception of certainty that when you do a calculation like this and you present a factor of safety like this, it's clearly presenting to the client and all the various stakeholders that will read the report that there's a certain level of certainty here, since you're quoting it to 3 decimal places. And designs evolved from the initial prescriptive and then moving to more precautionary design. And what this is the prescriptive combined with the observational method. And so any performance that indicates potential failure is identified and it's monitored to determine if mitigation measures are needed. That's the sort of simple concept of the observational. So running a prescriptive design and then combining it with the observational method. It requires some contingency design or action that can be implemented in a timely manner, but it's reactive. It's based on the observations. It's effective when the variations in performance can be foreseen and remediation measures identified and implemented in advance. It's not appropriate when you have a brittle failure mechanism, such as the Brumadinho video that we saw, because after all, there was very little signs of distress. There was no impending failure mechanism occurring, and so there was no time to respond. And here's an example. So that same sort of example I'm going to use, where you've got this upstream constructed tailings dam, you've got piezometers in the tailings, and in the starter dam, you've got an inclinometer survey, you've got INSAR, and you've got observations of seepage and cracking as a typical example. But it's not appropriate for brittle failure mode because Brumadinho had all of these. They had piezometers, they had survey, they had some inclinometers, they were using INSAR, they were observing seepage, and it was being inspected on a regular basis. But all of that did not help or negate the fact that it did in fact fail quite suddenly. So that precautionary approach has evolved to sort of a more performance-based design. And so it's a natural extension of the observational method. It requires detailed modeling to forecast the behavior and verify it with observation and surveillance. It's only possible because of advances in monitoring and analysis. So we now have remote sensing, automated processing of the sensing, and of course, complex numerical simulations to predict the behavior. It's focused on observable relevant parameters and characteristics, such as deformations, pore pressures, seepage and cracking, etc. It requires a certain level of significant rigor. And again, it's not appropriate when you have a brittle failure mechanism. So its designs are particularly in the mine tailings, and that's what I'm going to talk to, but I think it will be true for many areas of geotechnical design. It's moving towards a risk-informed design approach. And in the mine tailings, it's driven in part by these recent brittle failures. I showed you Brumadinho, but the failure of the Fundão tailings dam in 2015 was also a brittle failure mechanism. So two big tailings dam failures that were both brittle failure mechanisms that really made the industry sit up and rethink how it was doing things, and it's moving towards a risk-informed approach. So it's based on probability and reliability concepts, and I will briefly review some of those basic concepts. It uses a target annual failure probability or target reliability index to verify margin of safety, and it's informed by appropriate assessments of risk and uncertainty. So what is risk-informed design? And so before we get into that in detail, it's worth just covering basic elements of uncertainty and probability. And here I'm going to draw quite heavily from some publications that Suzanne Lacasse has done. She's published quite extensively on probability and risk. And so many of those papers are very useful. I've taken an excellent one that she put together in 2019 for the European conference. And this is a frequency plot of, say, undrained shear strength. And you see a sort of classic histogram where you've got a mean and a standard deviation of the undrained shear strength. And of course, you've got a coefficient of variation, which is that standard deviation divided by the mean. And the uncertainties, or how wide or how large that standard deviation is caused by two major things. One is, I tend not to like these fancy terms, but the aleatoric uncertainty, which is due to variability. So the natural randomness, and soil, of course, is naturally variable. And so we deal with this natural randomness all the time. We can't reduce it. However, we can understand it more by doing more testing to quantify that natural randomness, that variability. And then we have epistemic uncertainty, and that's really lack of knowledge, such as measurement uncertainty, as well as model uncertainty. And this can be reduced. If we do better tests, better interpretation, we can reduce this epistemic uncertainty. But there'll always be some level of uncertainty. And Suzanne showed this quite nicely in this nice simple diagram that shows the variation of the resistance in green, and then the variation of the load. And although the resistance, the mean value of the resistance is larger than the load, there is a certain area that overlaps. And so there's always a finite probability that failure could occur. If the resistance is smaller than you think and the load is bigger than you think, there is a possibility that that failure could occur. And the probability is essentially the area under that curve where the two cross over. So both load and resistance have uncertainty, and failure probabilities relate to the overlap of those two uncertain distributions. And Suzanne also shows this nice plot. I like this plot because it shows two examples. You have one example where the mean factor of safety is relatively low, it's 1.4, but the level of uncertainty, the standard deviation is small, so it's got a relatively small uncertainty. And so this factor of safety has a probability of failure of 1 in 10,000. So it potentially could fail once in 10,000 years. And then you have another one which has much larger uncertainty. It does have a larger factor of safety, so the mean value gives you a larger factor of safety of 1.8, but the probability of failure is now really just 5 times 10 to the minus 2, or 5 times in 100 years, or once in 20 years. So there's a big difference between that high factor of safety, but it actually has a probability of failing once in 20 years, compared to the lower factor of safety that has a probability of failing once in 10,000 years. So high factor of safety does not necessarily imply smaller risk, and it depends on the level of uncertainty. In other words, the knowledge that you have about the problem is not necessarily linked to the level of uncertainty. You may know a lot about that case that has a factor of safety of 1.8, but the various uncertainties, whether or not they're aleatoric or epistemic, result in a large level of uncertainty, and so a higher probability. Now, Silva and his colleagues in 2008 tried to look at historical cases and they combined historical and subjective probabilities for engineering practice. And they came up with this sort of attractive diagram that looks at annual probability of failure as a function of factor of safety. And they defined 4 categories, basically from best practice down to poor practice. And they sort of talked that best practice would be designed, built, and operated to a state of practice, and then all the way down to the poor one, which is little or no engineering. And you can see the examples that they used to classify that. But because knowledge and uncertainty are not linked, in a way, it might be better to think of this in terms of the best practice is really when you have low uncertainty, and the poor practice is where you have high uncertainty. And that's not linked to knowledge. And so you could well have a condition where you have very good knowledge with little uncertainty, and that would be the upper one. But you could have relatively good knowledge, but with large uncertainty. So 3. So 1, 2, and 3 all could have relatively good knowledge. It's just that they have large levels of uncertainty. And again, not always applicable to brittle failures. And here, what I've done is that L. Ramley did his PhD at the University of Alberta under Professor Morgenstern, and he looked at 10 case histories, and he was using limit, equilibrium, and probability analysis to determine the probability of failure for these 10 case histories. And so he was able to plot these on here. And I've added them here. He didn't actually add them to this plot. I've added it to the plot. And it shows that his case history do fit the general trends of this plot, but only when you think of it in terms of uncertainty. So some of these cases, there was best practices were being done, and a lot was known about the site, but they basically acknowledged that, particularly in examples when it dealt with undrained shear strength. So whenever they were dealing with undrained shear strength of a fine-grained soil, there's large uncertainty of exactly what is the value of undrained shear strength. Even though you did a lot of field work, CPTs, took samples, a lot of lab testing, there's still a high level of uncertainty. So knowledge and uncertainty are not necessarily linked. And in fact, if we go back to that example I showed that had this factor of safety of roughly 1.3, you can see that if there's high uncertainty in the peak undrained strength, it could be a risk of 1 in 5 years, one failure in 5 years. Or if there was a very low uncertainty, it could be as low as 1 in 10,000 years. But because it's peak undrained strength, we generally sort of move towards higher levels of uncertainty. And so you fit down into these higher annual probabilities of around 10 to the minus 1. And that was using peak undrained strength. So when we talk about risk, what does risk mean? Risk is really this combination of likelihood of failure and the resulting consequences. It's the sum of those two. So it combines the probability and the severity. And in simple terms, it addresses 3 questions. First of all, what can happen? What can go wrong? How likely is it that it could happen? And then if it does happen, what are the consequences that could occur? So risk is higher when the likelihood and consequences of failure are higher, and risk is lower when the likelihood and consequences are lower. So it's the combination of the two. And you'll see later that in many cases, it's driven more by consequence than it is by likelihood. Now, when we look at deterministic analysis, which is common in a lot of geotechnical engineering, that prescriptive approach we showed was purely deterministic. It's suitable when there's little uncertainty in failure modes or parameters or forces. No randomness is involved in estimating the future states. It aims at demonstrating that the facility is tolerant to identified hazards within a design basis, and it evaluates some nominal performance. It does not consider the full range of possible outcomes, nor quantifies the likelihood of such outcomes. And of course, it may underestimate the risk. So we've got probabilistic analysis, and they're obviously more suitable for when you have uncertainties that govern the design. And really that applies to a lot of geotechnical problems. We deal in a lot of uncertainty. And so in many respects, geotechnical engineering is moving towards a more probabilistic type approach and moving away from deterministic. It attempts to include all possible scenarios, their likelihood and impact. it's comparable to a series of sensitivity analysis. I quite often recommend that people at a minimum do a series of sensitivity analysis. And it's relatively easy to do a relatively large number of sensitivity analysis. That doesn't actually quantify the risk and uncertainties, but at least it begins to bracket the likely outcomes. If you do a probabilistic analysis, it provides an estimate of risk and uncertainty, and probabilistic risk assessment helps understand and account for uncertainties. And more importantly, it encourages a debate that should lead to more insight and robust decisions. So the process of a risk assessment using probabilistic analysis at least gives you insight. So in the tailings world, the ICMM produced this tailing management good practice guide, and they talk about a risk-informed design, and it's made up of these components of risk assessment, which is first to a risk identification, followed by a risk analysis and a risk evaluation, and then moving on to risk management, and then the communication of risk, and then surveillance and review, and then based on that surveillance and review and performance, update the risk assessment. So it's a circular process. It doesn't mean you stop doing surveillance and monitoring. That continues to be an important part, but it's part of this cycle of the risk-informed design. And I've taken these slides from the International Council on Mining and Metals, since they're quite nice. So under risk identification, the first steps is to identify site-specific potential failure modes. So you look at the natural hazards, such as earthquakes, extreme weather events, possible landslides, etc. Any hazard that could impact the site. You look at how that would impact on the structure, such as slope instability, overtopping, internal erosion or piping through the embankment. And then you also look at operational events here, for example, failure of a tailings pipeline. So you look at all of these risks that could impact the structure. And then you identify potential failure modes. So you run a potential failure modes analysis. And here the goal is to try and identify credible and non-credible failure mechanisms. If they're non-credible, you rule them out. If they're credible, you bring them forward to estimate the likelihood and the resulting consequences. So the risk analysis, there's sort of three broad approaches. One is a purely qualitative approach. It's subjective estimates through consensus of experts. And then there's a semi-quantitative method, which involves calculations as well as consensus of experts. And there are various ways to do that. The one I've shown here is an event tree, and I'm just illustrating again from one of Suzanne's papers. It's a very nice sort of summary of an event tree where you look at some triggering mechanism, whether or not it's strong, intermediate, or weak. You look at the geotechnical conditions, whether or not it could lead to failure, and then eventually what the consequence could be and what the ultimate likelihood or probability of that sequence of events. And then, of course, you can also do a full quantitative analysis, which involves a full probabilistic analysis, such as Monte Carlo simulations. This is obviously a lot more involved, and not all problems are suitable for a full probabilistic analysis. And the trend is to move away from qualitative and more into semi-quantitative and heading towards more quantitative methods. Now, when it comes to looking at consequence, so this is a consequence classification matrix. Hopefully you don't have these things blocking your view that I have it for me. And so the Global Industry Standard on Tailings Management, GISTM, developed this consequence classification. It's similar to others, but I've just chosen this as an example. So it's got 5 grades from low all the way up to extreme, and it looks at population at risk, potential loss of life. This is environmental, and then you've got social and cultural, and then you've got infrastructure. And at the end here, I've added that maybe even you could add another table of reputational damage. You know, particularly in the mine tailings industry, if you have a significant failure, then there's a loss of reputation, and maybe that should be considered too. But if you look at it, you start to look at anything significant, anything that's above high is going to involve a loss of life. High is anywhere between 1 to 10. Now, significant is unspecified, but one could argue that doesn't that essentially mean one loss of life. It's a bit vague on that, but so certainly any classification greater than high is going to involve loss of life, significant environmental damage, and significant, less than $100 million worth of infrastructure costs, etc. Now, GISTM also has design criteria, and it talks about during operation and active care closure, and then eventually into passive care closure. And depending on the consequent classification depends on the level of design. Here it's for flood, this one is for seismic. But what you notice is that when it comes to closure, it all goes to 1 in 10,000 years. So it's basically saying that when you're designing something like this, you need to design with closure in mind, because eventually you're going to have to design for 10,000 year events. And so, possibly you need to keep this in mind even during operations, because eventually you're going to have to go there. So it can be more cost effective if you start the process during operation and design. Now, when it comes to risk mitigation and communication, these charts have evolved. This is a chart that was sort of often quoted as Whitman. It actually came from others. Whitman was the first to sort of publish it, and then Davidson updated it in 2015. But it's sort of a frequency consequence chart, often referred to as an FN chart. Most of the charts, they tend to focus on either dollars lost or lives lost. This one is lives lost, and it defines an area of acceptable risk. So these green lines down here says anything above and to the right, below and to the left is acceptable. Anything above and to the right would be unacceptable. And then the US Bureau of Reclamations sort of updated it, and they also defined a region that they refer to as the ALART region, as low as reasonably possible. And so you've got probability on the vertical axis here, again, number of fatalities, and it's got a starting point of 10 to the minus 4. And that sort of originates, and Suzanne showed it in her 2019 paper, that the annual probability of dying, at least based on Statistics Canada, is about 1 in 10 to the minus 4 in the early years of your life. And I often think that, 1 in 10,000 mortality rate for children, sometimes it's regarded as sort of that's the acceptable societal limit. But really what it boils down to, if your child dies, it's unlikely that you're going to think that it's an acceptable risk, even though it statistically is the average value. And it also highlights the sort of a 1 in a million probability is essentially the limit of estimation. It becomes very difficult to estimate anything beyond 1 in a million. And so when it comes to communication, this traffic light system has become quite popular. And here it is in terms of a qualitative risk assessment. And so you've got some hazard category on the left from high down to very low. And then you've got subjective consequence categories from 1 to 5, again, 1 being low, 5 being high. And so the red region is obviously high consequence and high likelihood, and you want to avoid that area, and you'd ideally want to be in this area of low likelihood and low consequence. But it's too qualitative if the consequences are quite high, which, as you saw, as soon as you start talking about a loss of life, you're into the high consequence region. And so these quantitative risk assessments can have a similar sort of traffic light system, but now you can see that you've got actual values. So instead of subjective categories of probability, you've now got real probabilities from 10 to the minus 1, which is a very high probability, a 1 in 10 chance, all the way down to a 1 in a million chance. And you can see the red and green. You can see I've made the red area larger using the GISTM consequence category that says, well, you want to have a larger red area as possible. And what we're seeing is that stakeholders, of course, need to define their risk tolerance. In other words, how big should that red area be? And the only people that can really make that are the stakeholders. And When it comes to risk tolerance, what you're finding is that many mining companies have stated goals of zero harm. This image on the right, I actually took this photograph at a mine site because it was on the wall, and it was the stated goals, and the number one stated goal was zero harm workplace, and this is quite common. And so they're stating that their goal is zero harm. And the global industry standard on tailings management, GISTM, actually has a zero tolerance for human fatality. And so it's clear that these are aspirational goals, because you can't guarantee that there will be absolutely no loss of life, because accidents do occur. So it's clearly an aspirational goal. But what it says is that owners are increasingly defining this zero tolerance for risk. And when you put that onto this traffic-like system, what that essentially says is that nearly everything goes to red other than the low consequence category. Remember, low consequence is no loss of life. Significant could be 1, and high would be between 1 and 10. So a large portion of it starts to go red. And when that happens, it really sort of says, so the probability of failure has a smaller role, and it's more controlled by the consequences. So basically what it says is you must design away all the failure modes and or reduce the consequence. So you've got to reduce the likelihood of failure down to extremely low values, and it becomes dominated by the consequence of what could go wrong. Now, many years ago, when I talked about site investigation, I had sort of said that the complexity of site investigation should be based on the level of risk of a project. And here I sort of qualitatively said, well, if you had low risk projects, you could take a sort of fairly simple approach. And when it came to high risk projects, you often do a phased investigation. You start off with some simple geophysics and in situ testing, and that is usually followed up by more detailed investigation that could involve additional in situ testing, and usually collecting high quality undisturbed samples, high quality lab testing. But since it's difficult to get large numbers of high quality samples, and it's costly and time consuming to do a lot of high quality lab testing, often this is in rather limited number. And so you often have to then tie it back to the in situ testing, like the CPT, and get a site-specific correlation for this high-risk project. So for tailing structures, since they're constructed over time, the risk evolves over time. So often when the project starts, the risk is relatively small. The structure could be quite small. It might have a compacted starter dam with very little water behind it. So the consequence of failure is very low. But over time, as the structure grows inside, the consequences increase, so the risk increases. And so, of course, the level of site investigation should be progressively increased in complexity and sophistication commensurate with the level of risk. So now I want to get to looking at an example. And so I'm going to use this example. It's a tailings embankment. It's upstream construction. It's a ring impoundment. It's about 4.5 kilometers long. I won't tell you exactly where it is, but I've been involved in several projects that have sort of similar geometry. So this is not that unusual. This one has a consequence classification of very high. It has a starter dam to about 15 meters high, compacted residual soils. The foundations are residual soils. And then it went upstream construction in 2 9-meter lifts with a goal of maybe going higher. And there was cell raising. So they had a sort of a cell construction that would try to deposit coarser, slightly denser sand in the cells, and then the looser tailings behind. And as I say, 4.5 kilometers long. I'm just looking at one example of a cross section. So they did CPTs and seismic CPTs. So they did some CPTs near the crest on the tailings, through the cell, and then out in the pond, and then through the first raise, and then also through the starter dam, the compacted starter dam, and also at the toe into the residual soils. And what we see is the tailings are predominantly fine-grained. They've got fine content greater than 50%. The plasticity index is generally less than 7%, and in cases non-plastic. And essentially it's interbedded sands and silts. And if you look quite closely, you can see the interbedded sands and silts. Each of the spikes up tends to be a sandier layer, and the dips down are the fine-grained silt tailings. And they're generally contractive. The starter dam is dilative and the foundation residual soils are dilative. And here you can see I've just shown an example of the soil behavior type chart, and you've got the collective contractive dilative boundary, and you see that on this particular CPT, most of it plots in the contractive region. The little bit that's dilative is the upper portions of the cell construction, the sand cell, but most of it is relatively fine-grained silts and clay-like material, and it's all on the contractive side, relatively typical for hydraulically placed tailings. If you look at the phreatic surface and piezometric surface, there were relatively frequent dissipation tests. Most of them were relatively rapid, which indicates risk of partial drainage in the sandy tailings. But what you tend to find is the coarser tailings is almost free draining, and the finer silt tailings is undrained. So you get these spikes in pore pressure every time it goes through a silt tailings, it's undrained, and the coarser tailings is either partially drained or fully drained. Frequent dissipation tests show that there's a piezometric profile that's less than hydrostatic. In this case, it's nominally about 70% of hydrostatic. So this arrow is indicating a slightly downward flow. And you can see that the excess pore pressures, I'm showing the piezometric profile in blue, and you can see that the excess pore pressures are generally positive due to the contractive nature in the tailings, and then they're negative in the compacted starter dam, and they're negative in the residual soils. So the CPTs and the pore pressure are giving quite a bit of information. I threw this in because it's common for people to go and install, say, vibrating wire piezometers. But when you have downward flow, if you have a single piezometer, that single piezometer will give you a head of water pressure at that point. But if you've got downward flow, it's less than hydrostatic. And so if you take the head of water that you're measuring at that depth from a single piezometer, you can underestimate what the real phreatic surface is. And I'm illustrating it here in sort of orange compared to the real one in blue. And so you need at least two piezometers vertically to get some understanding of the gradient. And of course, ideally, if you've got a CPT where you did multiple dissipations, you already know the gradient. And so you can take that gradient and then adjust the actual head that you're measuring in the piezometer and get the true phreatic surface, or the true surface where saturated tailings exist. Now, in an extreme case, if you have very strong downward flow, almost vertical flow straight down, then the head measured in a piezometer could be extremely low. So in fact, you could have what would appear to be almost a dry piezometer where the head is essentially zero. And some people would look at that and say, oh, well, the tailings are dry. And it says, well, not necessarily, because if you know that water is being placed in at the top, so you know water's at the surface and it's flowing vertically down, you just have a vertical piezometric surface that's essentially zero. And so the tailings could be essentially saturated, but the head at a given depth is close to zero. So it can be very misleading looking at single piezometer values when you're trying to grasp the overall flow mechanism and where the level of saturation is. And because of seismic CPT, increasingly people are measuring P-wave velocity and saying, well, the P-wave velocity I can use to determine whether or not it's saturated. And when I measured the P-wave velocity, it showed that it wasn't saturated. So, you know, it's either dry or it's unsaturated. But the difficulty there is when you look here at the P-wave velocity as a function of degree of saturation, you can see that 1500 meters per second is roughly the typical P-wave velocity in 100% saturated material, and it drops markedly. And so by the time you get to 95% saturated, it's close to about, in this case, 500 meters per second. So 1/3 of the value, but it's still 95% saturated. So research has shown that when you're anywhere from sort of 85% up to 100% saturated, in that region there, it's not 100% saturated, but you have small air bubbles. So in this region of sort of 90 to 95, it's going to behave as it's saturated. The P-wave velocity is low because you've got these small little occluded bubbles. But that if you shear this material and it's contractive, as it contracts, those air bubbles almost immediately go into solution and the material will behave as if it's 100% saturated. And that's true whether or not you have cyclic loading or static loading. If the material is contractive at large strains, then those bubbles will go into solution. And that's what the CPT was showing, because when the CPT is pushed in, it compresses the soil ahead of the cone, and it could be like 90% saturated, but it pushes it to close to 100% saturated, and you start to measure excess pore pressures quite quickly. So be cautious using P-wave velocity to determine if it's saturated, because it can behave saturated even if it's not 100% saturated, because you've got these small occluded bubbles. And then if you look at the undrained strength, so the tailings are essentially normally consolidated. If you joined up all the points of the fine-grained silt tailings, they show it's essentially normally consolidated with a peak undrained strength of normally about 0.22. And it also shows it's got a high sensitivity of 3 to 4. And so there's clearly a potential for strength loss in undrained shear. So if undrained loading gets triggered, then you run the risk of a fairly significant strength loss. And that's indicated up here. These are the contours of the residual undrained strength ratio. And you can see that they're generally ranging from 0.05 up to 0.2, varying, but statistically it's below 0.1. In fact, that's illustrated on this next slide. If I take two of the CPTs and I run statistics on the residual undrained strength, this is just based on one interpretation method, but it shows that it's somewhere between 0.05 and 0.15. And there's a high level of uncertainty. And what we saw was that potential failure surface that we looked at right at the beginning, the one that had, when you were using a peak undrained strength of 0.27 as the undrained strength ratio, the factor of safety was about 1.3. And you can see that nearly all of the failure surfaces running through saturated tailings. And so you could almost do a sensitivity analysis in your head, in the sense of the factor of safety is almost directly proportional to the undrained strength ratio. And so if in the initial case, it had an undrained strength ratio of about 0.27 and a factor of safety of 1.3. So if I drop that undrained strength ratio from nominally 0.3 down to 0.15, then the factor of safety nominally goes from 1.3 down to 0.65. Because nearly all of it is through the unsaturated material. But it's clear that the factor of safety is significantly less than 1 for any one of these ranges of residual undrained strength. And that was just looking at the tailings. If you look at the residual soils in the foundation, these are residual soils, so they're not mechanically over-consolidated. They have a yield stress or an apparent OCR, due to the residual bonding. And here I'm showing a number of CPTs that were done through the foundation. And on the right-hand side is the interpreted yield stress ratio. And you can see it's highly variable, but in this particular case, from roughly about 2 meters down to almost 4 meters, the residual soil looks a little bit weaker, and the OCR, or the yield stress ratio, is in the order of 5 to 10, and a couple of them are around 5. And so a yield stress ratio of about 4 to 5 is right on that boundary between contractive and dilative. Anything less than 5 is going to behave in a more contractive manner. And so it says that under its existing stresses, under just 2 meters of overburden pressure, it's lightly over-consolidated, and it's marginally dilative. And the CPT indicated that the pore pressures were on the dilative side, and it was interpreted as a dilative material. But under the weight of the embankment and the tailings, so there's almost 30 odd meters of tailings. And so that would push this residual soil closer to the normally consolidated region. And so portions of the residual soil will in fact be almost normally consolidated under the tailings, and therefore have an undrained strength that's lower than the drain strength. And ideally, you should be putting in an undrained strength. But you can see, again, high level of uncertainty of exactly what strength should be applied under those conditions. So the real issue comes down to is, will undrained behavior be triggered? Because we were talking about undrained strengths, and currently, of course, the tailings dam is sitting there. It's behaving in a drained manner. It's behaving perfectly well, no signs of distress, no movements, etc. So everything seems to be behaving well, just like Brumadinho was. But could some event trigger it to behave in an undrained manner? And if it does, it could then potentially strain soften to these extremely low residual values with very low factors of safety. So when we look at case histories, Brumadinho was example. So I'm showing the two here. So the top one is Fundão, and 19 people died. And the failure mechanism was essentially an unknown slimes layer that triggered the undrained response. And then below is Feijão, the Brumadinho one, and there was sort of unknown light bonding that was potentially a role in why the material was so brittle, and that resulted in over 250 deaths. So both of them were very brittle failures, little or no warning. Observational methods was ineffective. The triggering mechanisms were extremely small and often quite complex. And the consequences were very extreme. There was loss of life involved, significant financial costs, in the order of tens of billions of dollars, major environmental damages, as well as, of course, criminal charges have been put against some of the engineers and the executives. If you look at the case histories for foundations, and I didn't want to just limit it only to the tailings, but Mount Poly was a foundation failure, undrained failure through the foundation. It again was a brittle failure, relatively little warning. The observational method wasn't effective, and the consequences were quite extreme. Major environmental damages, high litigation costs, engineers lost their license to practice. And that was an undrained failure through the foundation material. Similar to that residual soils, it was an over-consolidated material that, due to the weight of the tailings and embankment, was pushed into its normally consolidated region and was behaving contractive, and therefore the undrained strength was significantly lower than the drain strength and eventually led to an undrained failure. So when it comes to analysis, you could run a limit equilibrium analysis. You could do deterministic, but that's unreliable if you're dealing with strain softening behavior. And there's uncertainty in terms of how do you select the representative parameter. You could see that obviously the peak undrained strength has a large level of uncertainty, as does the residual undrained strength. So they both involve significant uncertainty. And you cannot determine the likelihood. You just calculate a factor of safety. Now, you could run a probabilistic analysis using limit equilibrium, like El Ramli did. It's still unreliable if you're dealing with strain softening behavior. And of course, even if you do it, it could require a significant number of runs in the order of thousands of runs to try and give you an example. And here's an example from El Ramli's work for one of the cases of looking at factor of safety from limit equilibrium in a probabilistic manner. You could run advanced deformation analysis, likewise deterministic, but again, it requires an appropriate constitutive model, which could be quite difficult if you're dealing with strain softening material. You also, again, have uncertainty about what do you select as your representative parameter and the distribution of that parameter. Also, it can be very challenging to model all the possible triggers, because these case histories have shown that some of the triggers are extremely small and complex, so they can be quite difficult to model accurately. And then, of course, you can't determine the likelihood on a deterministic deformation analysis. Or you could run a probabilistic, which is what we did for Brumadinho. Of course, we had the advantage, we knew the endpoint, we knew that it failed, so we were calibrating everything to that failure. So it was a little bit easier, but even so, we did run a full three-dimensional probabilistic analysis with a variable distribution. In this case, it's showing state parameter, but state parameter was linked to the constitutive parameters. And so we were running an advanced deformation analysis in a probabilistic manner. It can be, again, difficult to determine the representative variability and uncertainty of all the parameters, a challenge to model all the trigger events, and again, may require thousands of runs. For Brumadinho, we didn't need to run thousands. We actually ran 40 different models because we were trying to find the four different models of distribution, stochastic distribution of parameters that gave the lowest factor of safety. So where the structure was marginally stable under its peak undrained shear strength. Now, when it comes to this semi-quantitative, I talked about a risk using an event tree, and I wanted to just talk briefly about that because event tree analysis provides some useful insight. Here I'm just showing an example. Don't take too much credence on the actual values, they're just examples. So you start with some trigger event that could be, say, an earthquake or a flood. Here I'm going to show just the earthquake. And so you start with like a 10,000 year earthquake, which in this particular one has a PGA of about 0.18 G. Now, the key when you're dealing with a material that's contractive at large strains and has a potential for significant strength loss if triggered to behave undrained, when it comes to the seismic triggering of that, quite often people run traditional triggering mechanisms, simplified triggering approach. Now, the problem with that is the simplified liquefaction, cyclic liquefaction approach was designed for level ground conditions with no static bias. Now, when you're dealing with a slope, such as a tailings dam, you have a significant static bias. And so if you have a material that is contractive at large strains with a significant static bias, then the correction for that static bias is significantly less than 1. So although you might run a simple simplified triggering mechanism, quite often people seem to forget that they need to add in that K alpha correction for static bias, which is usually significantly less than 1. And when you do that, you find out that really it can be quite small earthquakes that can trigger. And over on the right, I've added a little note that basically any event that exceeds the threshold strain can trigger strength loss. So this 1 in 10,000 has a probability of 10 to the minus 4. And so here I've assigned, well, it's an 80% chance that it will in fact trigger strength loss, and therefore 20% probability that it will not trigger strength loss. And so if strength loss is triggered, then I've assigned a 90% probability that it would fail, and that it would have an 80% that it would be an extreme consequence event, leading to that you've got 6 times 10 to the minus 5 probability of this extreme event occurring. But when you do that, you find that even that event is unacceptable. But when you realize that it's actually driven by what is the smallest event that will not trigger strength loss? So would the 10,000 year, sorry, would the 1,000 year event, would that also trigger strength loss? If the answer is yes, and the probabilities are similar all the way through, then of course the end result will be 1 order of magnitude smaller. So instead of 10 to the minus 5, it'd come out 10 to the minus 4. And so you basically keep progressing down to say, well, what event is going to be small enough that it will not trigger strength loss? So these percentages start to change. Instead of 80% probability that strength loss will occur, maybe you're going to eventually get to a spot where you say, well, there's an 80% chance that strength loss will not occur. And you work your way through. So these event trees provide useful insight into both the sequence of events, as well as giving insights into how important the likelihood is likely to be. And what you find is that often it's don't worry too much about the first number. It's really the order of magnitude. Each of the orders of magnitude is what dominates. It's not so much, is it a 10% chance like 0.1, but is it 0.1 or 0.01? What's the order of magnitude? So, in the example I was showing, it's sort of what are the risk and uncertainty? And basically it says that if the consequence is significant or higher, in other words, if there's a risk of loss of life, basically you have to assume that a trigger will occur during the life of the structure. And the event tree can help you get to that logic. But in the end, you have to be prudent and say, look, it's the consequence that's dominating. And really, I have to assume that the event will occur and therefore proceed accordingly. And of course, part of that, it may be difficult to convince stakeholders, such as the community downstream, that some advanced numerical analysis that you ran is 100% reliable and that they can safely live downstream based on that advanced analysis. And I'm fortunate that I work on a number of review boards with Brian Watts, and Brian has occasionally made this excellent statement where he says that, you look, the bottom line is a rock buttress is more reliable than advanced deformation analysis. So although we are making significant advances in deformation analysis, and I'm not suggesting you don't run them, I think they are extremely useful for providing insights into the mechanisms, etc. But in the end, in the example I was given, as Brian said, in the end, that rock buttress is going to provide more reliability than some advanced analysis that's trying to convince me that triggering is not going to occur. Not true across the board. It depends. Every project is different, but in the particular example I'm showing, I think it's true. So to conclude then, so in summary, geotechnical engineers should both recognize and embrace uncertainty, and that the design process is evolving from one that used to be more prescriptive, and it's moving to one that's more risk informed. So it's informed by the appropriate assessment of risks and uncertainty. It attempts to include all possible scenarios, their likelihood and impact. It provides an estimate of risk and uncertainty. It helps understand and account for the uncertainties. And what we're seeing is that it's strongly influenced by consequences and risk tolerance, more so than the details of the likelihood. And it encourages communications that should lead to more insight and robust decision-making. And also, although I've talked about mine tailings, this framework is useful for basically any size of project. Just the thinking process is applicable to virtually any design problem. So that concludes my talk. I'm certainly happy to take any questions and open it up to discussion.
Thank you, Peter. That's excellent lecture. So before we move to a Q&A section, and I would like to make another acknowledgement to our sponsor. So we have, although we don't have a slide here, but we have a sponsor, a platinum sponsor from Server, and a gold sponsor from Greg and Contact, WSP, and silver sponsor from Nickel. So appreciate their support. So now let's see, we have 7 to 8 questions so far. So we have 20 minutes. Okay. So first question is, Peter, have you reviewed the INSAR data that is publicly available? Have now seen 3 presentations from three different INSAR companies, all showing that Brumadinho's dam was deforming as far back as August before the failure.
Yeah, I forgot to mention that in the presentation. I'm glad you raised that question, because the report had a detailed section. It has an appendix on the deformation, which includes a detailed analysis of the INSAR. And what the detailed analysis of the INSAR showed was that there was ongoing deformation in the embankment, typical of most embankments. They're settling and deforming slightly, very small amounts, predominantly downwards and slightly outwards. And what the INSAR showed, if you looked at it carefully, it was linked to the annual wet season. And so what you would find is during the dry season, the movements would slow down. And then during the wet season, they would accelerate again. And then the following dry season, they would slow down again, and then they would accelerate a little bit during the wet season. And the failure occurred in January, which was sort of near the end of the wet season. And so if you look at the deformations, if you just focus on the INSAR near the end, it shows an acceleration. And so some people have published and said, look, we're seeing this acceleration. And so if you extrapolate that, you could have predicted that it would have failed. And it says, well, not necessarily, because if you look back in time, then you saw a similar acceleration in each of the previous wet seasons, and they didn't fail then. And so there was no reason to suspect that the acceleration occurring at the wet season at the time of the failure was any different than the previous ones. And certainly Paolo, that did the INSAR analysis, came to the conclusion, and it was confirmed by the panel, that the INSAR was insufficient to suggest that failure could have been predicted. The movements were consistent with previous movements in previous wet seasons.
Okay, next question from Alan. Glad you brought up a plan with a closure in mind. Not sure how often this is considered in general.
Nor am I. That's a good question. I mean, you're right. I mean, the traditional approach is often, people would look at the prescriptive design codes like that Canadian Dam Association one, and it would show that during construction, in other words, during operation, you could accept a lower factor of safety. And so that sort of continued on through, where people would say, well, we'll use sort of smaller return period events because it's only going to be in construction for 10 or 20 years. And so during that time period, we'll use smaller return period events. And then when we go to closure, then we'll design for the big event. But logic would say, well, you are going to have to design for that big event eventually. And so why not embed it into the design right from the beginning? And certainly in the people involved with closure and landform design, such as Gord McKenna and colleagues, they quite correctly push that right from the beginning, you should be thinking about closure. So right from the start, you need to have closure in mind about how you lay this thing out, how you're going to design it, what the geometry looks like, etc. I've been involved in a few projects where it always looks a bit strange. They have like a 2.5 to 1 slope on an embankment, and then as it moves to closure, they then regrade it to a 3 to 1, and they spend all that money to regrade it. And so it says, well, why didn't they build it to 3 to 1 to start with? But of course, that gets into issues of accounting, how they account for the expenditures, and people have written about this forward accounting where it's cheaper to spend money later than it is now, which therefore why not push the expenditure off? And also it's sometimes driven by the fact that you don't really know when closure is going to happen, and you don't know how the mine is going to expand, and so everything tends to be in flux a little bit, and so people tend not to want to commit to it. But when it comes to risk assessment, I think the risk assessment says, well, from a risk assessment, you should at least include that into your risk-informed decision-making.
Thank you. So the next question is, since uncertainty is not the same as variability, to actually calculate the uncertainty, don't all the variable parameter need to be known? For example, something that is impossible. That's the first. Yeah, two questions actually. So let me read it one by one. Okay. So this is the first question from this person. Yeah.
Yeah, I think what you're getting at is, I touched on it briefly when I said there's aleatoric uncertainty and there's epistemic, and aleatory, you could do more testing to get a handle on how variable the deposits are, but you'll never get rid of the epistemic one. And that sort of raises the issue that even if you go to a full probabilistic analysis, you still have the challenge of trying to actually define the mean and the standard deviation, the coefficient of variation of all of the parameters involved, and that's no simple task. That's quite complicated, particularly when you throw in model uncertainty, because various types of interpretation don't always provide enough information of what the level of uncertainty in the model is. So it's quite challenging. But hopefully you saw that the risk-based approach, particularly using tools such as event tree, guides you on that. Yes, you don't know everything, and in the end, you need to make an informed decision of what you think the likelihood is. And then eventually you end up doing a little sensitivity analysis that says, well, this particular node, we're making an educated guess on the likelihood, but we could be off. So how sensitive is the end result if we change that number by an order of magnitude, just to see how sensitive the end product is. And often you find out not always that sensitive.
Okay, so here's the second question: is if you're using a partial failure to determine the likelihood of a failure, doesn't that negate all the set specific geotechnical information, since the data may come from a set from different than yours, different geology, age, construction, practice, and quality?
I think what you're asking there is if you're using an interpretation where the data is coming from different, like an empirical correlation where it's coming from different sites. And yeah, I think this is it here, isn't it? If using past failures to determine the likelihood of failure, doesn't that negate all the site-specific data? Yeah, that's true. I showed case histories as a way of illustrating the points of when you had brittle failure of how the consequence dominated the thinking. It wasn't so much that you were estimating likelihood based on the case histories. I was just illustrating the case histories to try and identify the level of uncertainty and bring out issues about how severe the consequence was and how small the triggering events were. It wasn't that you were trying to estimate likelihood for your particular project based on the case histories, although when you go through a sort of a subjective estimate of likelihood, often the subjective tables, will call upon and say, well, how often have you seen this in the past? Has this occurred sort of frequently in the past or rarely in the past? And so estimating likelihood of future events can often be guided by how frequently you see things happen in the past. Similar things happen in the past. Obviously, each site is different. Each site has its own specific data, etc.
Okay, so I think we have a lot of questions popping up now. So the next question is, how do you consider the extreme condition due to climate change seen in the recent years, using partial failure to determine the likelihood of failure?
Yeah, well, it's interesting, when you come to extreme participation events, somebody's done a probabilistic analysis of weather events, and I think increasingly review boards are tending to take that data, and then often the question is asking, saying, well, how much bigger could we expect this event to be given climate change? Are we in a region where they're expecting that climate change will produce increased precipitation or decreased precipitation, etc.? So increasingly you're seeing that question being asked is, what is the role of climate change on these events, and trying to embed that into the process. But again, when you come down to it, sometimes you'll talk about great precision, where they might say, well, a 72-hour probable maximum precipitation event is 722 millimeters. And one could argue, well, the 22 millimeters seems to be overly accurate. It's about 700 to 750 millimeters. I'm not sure we have the precision to actually go to 722 millimeters. But I mean, you've got a starting point for your calculation, but understand that there's always a little bit of uncertainty in those numbers.
Okay, next question is pretty long anyway. So I will read it through. Understanding and accounting for the uncertainty is a must. However, as someone who has been performing deterministic and probabilistic analysis of geotechnical structures, I can report that the assumption that go into a quantitative risk analysis, distribution property, pore water pressure, seismic flood load, interaction of various failure modes, dominoes effect are highly uncertain. making a calculated probability of failure, PF, highly uncertain. Just as a reporting factor safety to 3 decimal place give a false impression of certainty, so does the reporting of a PF, probability of failure, to 4 decimal place. That is a reality that need to be acknowledged as we readily advocate for the risk-based approach.
Yeah, that's a good point. I'm glad I was able to read that rather than just hear it. But yeah, your point is well taken, and hopefully that was what I was saying, is that I was getting to the conclusion that the detail of the probability is less important than the consequence. And so you're right, whether or not it's a semi-quantitative or a quantitative risk analysis, you don't get hung up too much on the actual number you're calculating, but really the order of magnitude that you're coming up with. And then using things like event trees to put the sequence of events together, and then often using your judgment or collective judgment in terms of what you think is a reasonable value and a reasonable risk. But yeah, I agree with what you're saying.
Okay, next question. Excellent presentation. Can you discuss the brittle index value and how it should be applied in the stability analysis?
Yeah, okay. The brittleness index was suggested by Bishop, way back in the 1970s. And in recent years, I've suggested that it would be better if we called it a strength loss index, because that's exactly what it is. It's the amount of strength loss relative to the peak strength. So if you lose all the strength, you have a brittleness index of 1, or a strength loss index of 1, or 100%. And of course, if there's no strength loss, you've got a strength loss index of 0. And I've suggested that the word brittle in there implies how fast it occurs. And really, brittleness is a combination of the amount of strength loss and the strain over which it requires for that to occur. And so you can have a strength loss index, let's say, of 80%. So it's going to lose 80% of its strength. But if that strength loss occurs over a very small strain, then we could say that that's extremely brittle. If that strength loss occurs over an extremely large amount of strain, we could say that's more ductile. And so the use of the word brittle and ductile should be applied to the level of strength loss and the amount of straining required for that strength loss to occur. And what we see in practice is that highly plastic clays can be quite sensitive. They can have high sensitivities, but they tend to be very ductile because of their plasticity. They have a relatively large strain to peak, and then an extremely large strain to residual. And so if you build an embankment over extremely soft plastic clay, the embankment tends to creep and slump relatively slowly. And so the whole failure mechanism is rather slow and progressive. Whereas if you have a low plastic material like sands and silts, etc., they tend to reach peak at extremely small strains and then can experience strength loss over a very small strain. And so they have a high strength loss index and are highly brittle. And so, of course, in that particular case, like Brumadinho, you can see very little deformation occurring, and then suddenly it goes and you get extremely large deformations occur in a matter of seconds. And so I think brittleness index is a nice concept. It would be better if we called it strength loss index and save the word brittle and ductile to really link to how rapidly it occurs. And the Canadian Dam Association has a nice diagram in their recent publications where they try to quantify that both in terms of strength loss index and the strain over which it occurs.
Okay. Next question, given the very complex trigger mechanism leading to flow liquefaction, how can you elaborate inventory tree?
Well, that's why I wanted to show that example, because in a way that example laid it out as a way of saying, well, this in a way is what the event tree would look like, is I have some event first. And then will that event trigger undrained behavior and strength loss? And if it does, what type of instability results and what type of consequences? So the example was trying to set out, in a general sense, how the event tree is used to handle material where undrained strength loss and brittle behavior could be a major part. So in this particular one, it's saying you're going to have significant strength loss. We think it's brittle, which means if it fails, it could flow and have an extreme consequence. So all of that's built in to the event tree and the likelihoods that you put on each of these nodes. Hopefully that answered that question.
Okay, this question I just sent to me, so I don't think Peter you can see. So I'll read out. In non-tailings application of geotechnical engineering, how can we determine whether or not a brittle failure will occur based on a set investigation result?
Sorry, so say it again. I missed the beginning of it.
In no tailings application of geotechnical engineering, how can we determine whether or not a brittle failure will occur based on the set investigation result?
Well, there's two ways. One is that just the approximate empirical one is that how plastic is the material. We know that low plastic and non-plastic materials tend to be more brittle than highly plastic, and I stated that earlier. So that's a very simple empirical method. So getting moisture contents and Atterberg limits is a really good starting point. Obviously, when the risk of the project is quite high, ideally, you would like to get undisturbed samples and do lab testing. Now, if you're dealing with silts and sands, getting undisturbed samples can be quite challenging. And so, critical state soil mechanics concepts then sort of moves towards you can get disturbed samples and determine the critical state line, and then by estimating the state, determine how much strength loss you think is likely, and the lab test you do would give you some idea on how brittle that material could be. Now, the difficulty, if you're dealing with reconstituted materials, they don't have the same fabric as the material in situ. And so although you get the correct critical state, which is at large strains, you may not get the exact correct stress strain curve because you may not have the correct fabric. And if there's some slight microstructure, you may miss that in your reconstituted sample. So if it was an ideal world, you would try to get undisturbed samples. And so what you tend to find, of course, is that non-plastic and low plastic materials, very difficult to sample. Moderately to high plastic materials are easier to sample. And so those materials you can sample and have a better chance of getting undisturbed samples and doing high quality lab testing and following appropriate stress paths that mimic what could happen in the field to determine what the stress strain curve is like and to determine how brittle it is. But again, it's still somewhat subjective. And in the end, within a risk-informed decision process, you have to look at the uncertainty involved and the level of risk and consequence that could come with that uncertainty. In other words, you'll never get the answer exactly right, but you're going to be guided by all the data you collect. And in the end, use a risk-informed approach for decision making.
Okay, so we pretty much just right on time now. Maybe one more question.
I'm scanning. The good news is most of them saying thanks for a great presentation. I'm not asking a question. those are the ones I like most.
Yeah, I think 10 more questions, whatever. So a lot. So hold on, let me see. Can we develop a simplified thought or approach to be applied in common and probably simple project? We should always consider risk assessment for any geotechnical case, yet detail and effort of analysis in what will cause the engineer to shy away from such a consideration. What are your thoughts on this?
Ooh, that's a complicated question. I apologize for asking you to say it again. Could you? Maybe I should try and find it so I can read it simultaneously.
So latest the one below, I believe. It's Robert Egg given this question. So can you develop a simplified thought or approach to be applied in common and probably simple project? We should always consider risk assessment for any geotechnical case, yet detail and effort of analysis involved will cause the engineer to shy away from such a consideration. What are your thoughts on this?
Well, I mean, if I understand that question correct, Robert, is by showing that event tree, hopefully that's insightful to say, quite often on projects I do, in a sense, I mentally do an event tree. So I mentally go through the thought process about, well, what events could occur and what do I think the sequence could be and what are the likelihoods of each of them? And you can almost do it mentally. Obviously, it's nice to eventually put it on paper because it's a way of communicating the thought process. But the reason I showed the event tree is it is relatively simple and it's quite insightful and it provides a framework to do what we're trying to do. And that's why I discussed it as opposed to going into sort of Monte Carlo simulations, etc., all of which are quite elegant and useful to do, but not always applicable to all problems. Whereas I find that the event tree thinking can be applied to even relatively simple projects. Hopefully that answered that question. I'm sorry if I was a little vague.
Okay, I think we have to stop here. There are many more questions. So Peter has already left his email here. So you can send your question to Peter. So thank you, Peter, for excellent question and addressing all the questions. And thank you for all participating in the event.
You're welcome. Thank you.
So we're going to close.
And Chen, you can stop recording.
Oh yeah, hold on. I mean, how do I? Yeah. Oh, here we go.
On the bottom. Oh.
Yeah.